Have you ever seen a factory robot putting together a smartphone or maybe one of those super fast packaging lines and just wondered how? How does a machine move with that kind of flawless, impossible precision over and over again? Well, the answer is hiding in plain sight in a really cool field of tech called motion control. And today, we're going to break down exactly how it all works. Just think about it for a second. It's everywhere. You've got these huge robotic arms in a car factory, and on the other end of the scale, you have incredibly delicate instruments used in nanotechnology. All of it depends on perfectly controlled, repeatable movements. It's not magic, it's just some seriously brilliant engineering. And the answer to this question? It has a name. And that name is motion control. It's pretty simple when you break it down. It's a part of automation that is all about, you guessed it, moving machine parts in a super controlled and precise way. This is the core tech that really brings all of that automation to life. And it is absolutely everywhere. Motion control is kind of the unsung hero working behind the scenes in so many high-tech fields. It's why a robot can perform surgery with superhuman steadiness and why a machine can build a microchip. So what's actually going on under the hood of one of these systems? Well, to really get it, we need to look at its anatomy. Every single motion control system, no matter how big or small, is built on 4 key parts that all have to work together perfectly. It's almost like a tiny biological system. Let's follow a single command to see how it works. Okay, so it all kicks off with the controller. That's the brain of the whole operation. It figures out the exact path, the speed, everything the machine needs to do. That command then zips over to the drive, which acts like the nervous system. It takes that little low-power signal from the brain and amps it up into serious high-power energy. That energy is what juices up the actuator. That's the muscle, usually an electric motor, which does the actual physical moving. But here's the secret sauce. To make sure everything is perfect, you have sensors. They're the senses of the system, constantly feeding information about position and speed right back to the brain. This closes the loop and lets the system make tiny corrections in real time. It's this beautiful, self-correcting dance of information and energy. Now, let's zoom right in on that muscle component, the actuator. In most of the systems you'll see today, this muscle is a special type of electric motor called a servo motor. But here's the thing, not all servo motors are created equal. To really see what makes them tick, we gotta explore the main types out there. And if we look at a resource like the Siemens Motion Control Catalog, you can see they pretty much fall into 3 main flavors. You've got synchronous servo motors, asynchronous servo motors, and then a really special case we're gonna get to called linear motors. All right, so first up, let's put the 2 main rotary types head to head, synchronous and asynchronous. And the most important thing to get here is that it's all about picking the right tool for the job. They have totally different strengths. So at a high level, it looks kind of like this. Synchronous motors are the sprinters. They're built for speed, for agility, for incredible precision. Asynchronous motors, though, they're the workhorses. They're built for raw, robust power and all-purpose industrial work. The source material really nails the description for synchronous motors. It says they're for applications with high dynamic response, precision, and flexibility demands. Now, when you hear high dynamic response, just think of a machine that needs to start, stop, and change direction in the blink of an eye and do it with absolute pinpoint accuracy. So where would you actually see these things in the wild? Well, picture the frantic, precise dance of a robotic arm on an assembly line, or these super complex high-speed rollers inside a modern printing press. That's the home turf for synchronous servo motors, like the Siemens 1FT6 series. Okay, now let's flip over to their counterparts. The source material calls asynchronous motors out for being for more general applications. Right. These are the heavy lifters of the industrial world. They don't need that same lightning-fast reaction time, but they have to be incredibly powerful and reliable. You're going to find these motors, models like the 1PH7 and 1PL6, doing the really tough jobs. They're powering the hoists that lift massive loads in warehouses. They're driving the giant screws in plastic extruders. And they're the main power source in huge machines that just have to run 24/7. This table really sums it all up, right? On one side, you have the precision specialists, the sprinters. On the other, the powerhouses, the workhorses. The key thing to remember is that how they're built on the inside, whether they use permanent magnets or work by induction, directly decides what their mission is going to be out in the real world. But what if you need a level of precision that even a super high-end synchronous motor just can't deliver? Well, that's when you enter a whole new world, the world of linear motors. The easiest way to think about it is like you took a normal motor, unrolled it, and laid it out flat. Okay, and this is my favorite part. The source material says that with the right sensors, these linear motors can be positioned in the nanometer range. Let that sink in. A nanometer is a billionth of a meter. That is an almost unbelievably tiny scale. We are talking about the absolute peak of motion control precision. So how on earth do they do that? Well, it's all about what they get rid of. With a linear motor, there are no gears, no belts, no screws that can introduce tiny, tiny errors. There's no backlash, which is that little bit of wiggle or play you get in gears, and there's way less friction. The motor acts directly on the thing it's moving. It's this direct control that makes it even possible to manufacture something like a modern microchip, which has features smaller than a virus. So after geeking out on all these different types, you have to ask the big question, why does any of this matter? And it matters a lot. Because for an engineer designing a machine, matching the right motor to the mission is one of the most critical calls they can make. Because the choice is always, always a balancing act. How much precision do you actually need? How much raw power is required? And of course, what's the budget? You don't use a crazy expensive ultra-precise linear motor for a simple conveyor belt, and you sure can't use a general-purpose motor for assembling nanotechnology. So here's the bottom line. Getting this choice right is the difference between a machine that does its job perfectly for years and one that fails, causing downtime, wasted product, and a whole lot of money down the drain. This hidden world of motion control has very, very real-world consequences. Okay, so let's do a super quick recap of what we've covered. Motion control is that four-part system: brain, nerves, muscle, and senses that makes all this precise automation possible. The muscle, the servo motor, comes in different flavors for different jobs. You've got synchronous for speed and precision, asynchronous for pure power, and linear motors for when you need the absolute ultimate in accuracy. And that kind of leaves us with one last big thought to chew on. We've seen how these systems can position things down to the nanometer. Now, as artificial intelligence and our control systems get even smarter, what new things is this going to unlock? What challenges that we think are impossible today will become totally routine, all thanks to this hidden world of perfect motion?